Hello interwebs, welcome to Let's Fix Computers. I've got an old motherboard here. This is an Asus P5G41T-M. So this is an old LGA 775 motherboard, and this is dead, it's kill, most likely due to failed capacitors. So if we take a closer look at the board here, I'll just show you what those look like. So you can see we've got one over here next to whatever this regulator is doing. Might be PCH power, or more likely, I think that might be system agent actually, but doesn't really matter. The point is, you can see that this capacitor has clearly domed. It's got a dome on top instead of being flat, and you can actually see that some of the electrolyte has oozed out from in there, where the capacitor has overheated and failed and all the rest of it. And there's a couple more on the board as well. If we go down over here, down to the bottom corner, this guy, not really very leaky, but you can clearly see that that one has domed as well. These guys here, you can see these ones are nice and flat. Where are we going? There. Those are nice and flat, no problems at all. This guy up here, that's he's doming as well, so that guy's on his way out. So you can see that, you know, a lot of caps on this board are failing or have failed. So this is a very old school problem that we don't really see these days, because modern motherboards, unless they're really tat motherboards, use all solid state caps. And you can spot the solid state ones because they're these guys like this one here. So this guy here, you can see that that is just a metal can. It does not have a cross vent on top. That is not a sure thing. You can get electrolytic capacitors, that is to say a capacitor with a liquid electrolyte inside of it, that have a flat top like this, and the vent is on the bottom of the cap. However, by and large, for this era, these style capacitors should be solid state with no liquid electrolyte inside them. But this is kind of from a crossover era where they were just starting to use solid caps. And so on this motherboard here, they're using solid caps for all of the big power stuff. You can see that V-Core is all solid caps there as well. However, all of the non-primary capacitors, all the other power capacitors on the board, they're all just liquid electrolyte capacitors. So that is most likely what has gone wrong with this. What I'm going to do, just to start off with, I'm going to try and power this board up just to see what it does, because I don't actually know what state it's in at the moment. I believe it's dead, it's kill, it doesn't post. So we're going to plug that in and just try and reproduce that. And then my intention for this video is to recap this board. I'm going to replace all of these power caps. We're going to do all of the brown ones. I'm not going to touch the solid state ones because those should be absolutely fine. But we're going to replace all the brown ones. I'm also going to get this guy here. It's not brown, but it's a black electrolytic capacitor. We're going to get that one. And I'll probably do this brown guy down here for good measure. These other black ones around the audio circuit, here, and these guys with the golden stripe, those are low ESD capacitors for the audio circuit. I'm going to leave those alone as well, because they're audio capacitors. They're not doing big power capacitor jobs. They're fine. They're also nothing to do with whether the board works or not. So I'm not going to bother replacing those because I'll have to get a different kind of capacitor for there, and it's a hassle I don't need. Whereas all of these brown ones, I can more or less use the same series. I've just got to get the correct value for it. So let me just grab a power supply and stuff like that, and we'll power this thing up and just see what it does. Now, I wouldn't consider this to be a quote-unquote modern-day problem. And what I mean by that is, as I mentioned, because modern motherboards are going to be using all solid-state caps, the only kind of boards where you're probably going to see bulging caps like this are old motherboards, like this one. And they're not worth doing. Like, you could do this as a hobby project or a passion project. I'll tell you more about that in a sec. But this isn't really this isn't an economic repair from a repair business standpoint. The reason why I'm doing this one is because this board has sentimental value with the client. I don't know what that sentimental value is. My assumption is that this was most likely the first computer they built or something like that. And they're holding on to it because they've got fond memories because it was, you know, the first computer they built, or they had it at a time of their life when they were playing certain games or something, and they've just got fond memories of using it, so they want to keep it going. So, as I say, it's not the cost that we will go through to fix this board ain't worth it. But when it's sentimental value, it's a case of, well, it doesn't really matter what the cost is. If someone is willing to pay to have it fixed, then they're willing to pay to have it fixed. Which is why we are where we are. So, as I say, this is more of an interest video, I think, but the theory of recapping something does apply to a lot of retro gear as well. Recapping a board is very popular for retro repair. It's a very common process. I've replaced capacitors to fix stuff before, but I've never really done a full board recap like this, so that's where my interest comes in. Just looking for where I can plug in a beep speaker. Right, let's see what happens when we try and power this on. Right, so it powers up. Alright, it doesn't look like we've got a post. It hasn't given me any beep codes or anything like that, so seems to be dead. I'm going to turn it off, and I'm going to reset the BIOS by removing the CMOS battery for a bit, just in case, because like it would be interesting to see if we can get anything out of this at all. If nothing else, just because one of the other potential behaviors I would expect from this is just instability. If it had posted there, my next move would have been to leave it running mem test and see if it can get through mem test, that kind of thing. But it looks like we're not going to get much of anything. So I'm going to reset the BIOS just to prove that it's not that. And then next, I guess, yeah, we'll just try recapping it and see if that fixes it. I believe the original owner has tried different memory and that kind of thing. So I'm kind of rolling on the... Well, I should try different memory, shouldn't I? What memory is even in this thing? Good, it does have DDR3 in it. So yeah, I could stick a different memory module in it as well, just to prove that it's not memory. So yeah, we'll do that. We'll try the BIOS reset. I'll try a different memory stick just to absolutely prove that the motherboard has failed. And then we'll move to identifying the capacitors on this thing. So I'll be back in a moment, everyone. No, there's nothing coming through here, and it hasn't beeped either, and it should have done that. So yeah, I'm assuming that has not posted. Power off. I think this is DDR3. Yes, it is. There is some residual heat in the chipset heat sinks. Like, they're not warm, but they're not room temp either. So the board is alive. It's doing something. I wonder whether I should flash the BIOS chip as well, just as one last thing. Like, what I really don't want to happen is to discover that there was another fault with this board. And yes, the capacitors were all leaky and horrible, but they weren't actually causing a problem. Because I've seen computers with domed and leaking capacitors that are working just fine. And, you know, you open the computer up to do your visual inspection, like while it's turned on, and you see the caps and you're like, oh boy, those are really kill. But the computer is running and it's working just fine. So I really want to be certain that this board is dead before I actually do this. Because otherwise there's going to be someone in the... Like, if we recap this board and it doesn't post, and then I reflash the BIOS chip and that fixes it, was it really the caps, you know? Okay, looks like that's still not posting. Cool. Okay, I'm going to flash the BIOS chip because this has a socketed BIOS chip from the good old days. So it's really easy to flash it. All you need is a BIOS flasher. So let's pop this guy out down here. File's been loaded. And I shall write. Bam. Now, this thing is dead. Alright, well, let's replace all the capacitors from it and see what happens. Yeah, fine, okay. Well, that power cycle was interesting. We got a response out of it, which again implies that there's someone at home, just the board is probably just too unstable to work properly. So that's what I'm guessing. Right, so I've done a big Clive now, and I took a picture of the board and then printed it out so I could draw on it. And I've numbered the capacitors. So we've got 1, 2, 3, Where's 4? 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on across the page. And then I missed a couple, so 18 is up here and 19 is over here. Then I turned the page over and I went through all the ones. So I started at 1 and I looked very carefully at the capacitor on the board, and I'll show you a close-up just so you can see what I'm doing. And as you can see, that one is a 16 volt 100 microfarad capacitor. So 16 volt 100 microfarad. Then 2 was 6.3 820 microfarad, and so on down the list. And I actually found there was not nearly as much variation as I thought. Obviously, capacitor values, capacitors in general have like 20% tolerance. And in the vast majority of applications, you don't actually need to be vaguely on track with a capacitor. You basically only have to be within the correct order of magnitude, and it will probably work. So as a result, they can do massive simplification and cost savings by using the same component in lots of places. So as you can see, most of these are all 6.3 820 microfarad, and I went over them one by one. I was like, it's another one of those. So I actually found out we had 16 6.3 volt 820 microfarad, and these are all the problem ones. All of the bulging ones are these guys. Then there's a couple of these 16 volt 100 mics and a single 16 volt 420 mic, which was the black guy here. So we're going to replace all of them anyway. We could probably get away with not doing these ones, and I'll have a look and see what I can find first, because the issue is I'm going to buy my caps from eBay because I like to buy from familiar locations. If I ordered electronic components all the time, I'd be buying from Element 14 or Farnell's, or insert electronics component supplier of your choice here. But I don't have accounts anywhere, and I can't be bothered to set that up and pay postage, etc., etc. I like eBay, okay? So I could just order 16 of those, and that's probably going to be good enough. And you know what? That's exactly what I'm going to do, because you can clearly see that these are the guys that are failing. So I'm going to order 16 of those. So let's jump on eBay and find some. So one of the things that we have to consider as well, the other value that I haven't written down here, is what the ESR of the capacitor is. Now the ESR, which is equivalent series resistance, I'm not going to try and explain the technical details of this because, in short, I don't know myself. I've never had formal training in electronics, so when we get deep into the nitty-gritty theory, that's where you really come up against the weak points in my knowledge. However, the gist of it is that if we have a capacitor, so I'll just put in the symbol for capacitor there, this will actually be, one of them will be longer than the other because we're using an electrolytic. I can't remember which way around it. I think the longer plate is the positive. So let's call that the positive and that the negative. It might be the other way around, but it doesn't matter. What we've got is that this is not a perfect world, and the capacitor itself has internal resistances, like the wires and the legs going into it, the materials have resistance. So what we actually have is something more akin to this. It's a resistor that goes into a capacitor. Or the other way around, it probably doesn't matter. So we actually have a resistance in line with the capacitor. Now, what the capacitor is doing is, as a voltage goes into the capacitor, you never have an exact flatline perfect 12 volts, for example. The 12 volt line will actually have ripple on it. It'll be a wavy line that is about 12 volts. And what the capacitor is doing is, if our 12 volt line is, I need a ruler. If that line is exactly 12 volts, every time the voltage goes above 12 volts, it's going to charge that capacitor slightly. And every time it dips below 12 volts, the capacitor will discharge back into the rail. So what it's doing is it's absorbing the spikes and then releasing energy in the dips. And it's pushing down and nudging up to smooth out that power rail. Now, depending on how big or what frequency this noise is at, depends on what kind of capacitor you need. So if you have really low frequency ripple on a big power rail, then the capacitor doesn't need to be very quick. It doesn't need to react very fast. That's not a big deal. But if you were trying to filter out very, very high frequency noise, like these ripples were really close together, like that kind of thing, obviously, if there's a lot of resistance in the capacitor, it takes time for it to absorb that charge and release it. So it may not be able to charge and discharge fast enough to smooth out the ripple, in which case the ESR is too high. The other thing as well is that if the capacitor is fatigued, then its internal resistances will increase and the ESR will become very high, which also prevents it from doing its job. You might have a capacitor that, if you actually measure its capacitance, is completely fine, but if you measure its ESR, you'll find the ESR has gone through the roof. So even though it can store a large amount of energy, it takes too long to store and release it, and therefore is not fit for purpose anymore. So the ESR is not super important for these power capacitors. And what I will do is, basically any premium capacitor will probably be listed as a low ESR capacitor, which is almost guaranteed to be significantly superior to these capacitors. So I will just buy like Panasonic low ESR or something like that. And for the record, these audio caps down here with the gold strip on them, they're known as audio grade capacitors, but what they actually are is just low ESR capacitors, hence the reason why they have the gold stripe. That generally indicates that it's a low ESR cap. To my knowledge, there is no disadvantage to a low ESR capacitor other than increased cost. And because we're doing a non-economic repair job, we don't really care how much the capacitors cost. However, if you're making 1 million motherboards, each one having 30 or 40 capacitors on it, you want to scrape off every cent you possibly can on your build cost, your bill of materials. So therefore, if you don't need the capacitor to be ESR, why would you pay for it to be an ESR capacitor? You're going to buy the cheap one because it doesn't matter. So for that matter, we're going to go low ESR just to guarantee that it's going to be good enough for the job. It's almost certainly overkill. It's almost certainly unnecessary. However, because cost is not a factor here, we don't actually care. So let's switch over to eBay. And as you can see on eBay here, I've just bashed in 6.3 volt 820 UF, so microfarad. And immediately we're getting results for capacitors. So top here, low ESR, Rubicon. So, you know, Rubicon, Panasonic, that kind of thing. That's what we're looking for. 10 pieces, £2 plus 1.25 postage and packaging. So we'd have to buy 2 packs of those. This is probably ludicrously expensive because we're buying in small quantity. If you were buying from an electronics supplier and you were buying in high quantities, these would be a fraction of the price. Again, this is not an economic repair. I don't really care what these cost. We're not trying to do this in an economically feasible way. This is purely a theoretical repair. This is a because we can repair. So again, I know I can probably find them cheaper elsewhere. You get the idea. Let's just check that this is correct. 6.3 volt, 820 microfarad. So yeah, that's fine. The size doesn't concern me either. It's going to be about the same size. They generally are. And again, 105 degrees. So the temperature rating is, in order to meet its minimum time before failure, it should not exceed that time. Any run time at or above that temperature will drastically shorten the life of the capacitor. Again, lots of details. Not going to go into. This is not a deep dive into capacitors. So, yeah, okay, that looks good. That's probably what I'm going to buy. Let's just check if there's anything else here. There we go. That's it. That's what I'm buying. One of those, please. Buy it now. There we go. Your order's in. I'll see you guys when that has arrived, and we'll start removing capacitors from the board. See you after the cut. Capacitors have been acquired. Here's a pack of caps. We're ready to go. So these ones are Rubicons, and they're 6.3, 820 microfarads. So what I'm going to do now is I'm going to take a couple of the old capacitors off the board. and we'll just do some quick measurements on them and see if we can see anything interesting in terms of capacitance tests, LCR tests, and so on. Just in case there's any interesting numbers to show off there. There might not be. These capacitors might drop into a reader and they might look absolutely fine, especially because I don't exactly have precision instruments for testing capacitors. But, don't know, we might look at it and go, hey, look, there we go. There's the numbers that are out of spec. So we've demonstrated in numbers what this failure looks like, whether that's in a different ESD or a different capacitance or whatever. Right, so I shall switch on my soldering iron and I will take off a couple of caps and we'll do some tests and go from there. So I'm going to do this with a soldering iron because these are through-hole caps, so I should just be able to very easily soldering iron hero these. So I'm going to flow just a little bit of fresh solder onto the pins to get them moving easily because this will be unleaded solder. And if I put on some nice leaded solder, it lowers the melt point, makes it easier to remove the part. And then I should just be able to walk them out. So let's flow some solder on. I'll take out a couple at the bottom and then I'll go for a couple of obviously failed ones. There's that. So now we'll put that upright. I'll give you guys some better shots of this in a minute. I'm just doing a test run. And here we go. That's the capacitor removed. So let's do that again and try and give you guys a nice macro shot. There we go. That's another one out. So now I'm going to remove this angry looking fella here because that should be a prime example of a failed one. So this is the one where we should see drastically different numbers when we measure the values. So let's try that out. There we go. One angry boy extracted. Also keep in mind we should be paying attention to the polarity of these capacitors so we know which way round they went. Of course, I took a picture of the board before I started, so I have a full reference of what everything should look like. Focus. So yeah, I've got this reference for what way around all the capacitors go anyway. But yeah, strongly recommend you take a picture of something before you start working on it, so you've got a reference of what the start point was. Okay, let's do some tests and see what our baselines are. Here's my transistor tester, which is not a scientific instrument. This one is also uncalibrated because even though it tells you how to calibrate it, I've tried to calibrate it many times and it just doesn't seem to work. So I don't know. However, I use this for measuring capacitors and stuff like that. It doesn't need to be super accurate. It just has to be in the right ballpark, which is what I'm after. So let's put in one of the new capacitors and just get a baseline for the kind of readings we're expecting to see here. Now I need to, let's go across from 3 to 1. That should do. Whoop. So we put that guy in there like that and turn it on. And it will figure out what I've inserted and tell me about it. It's a capacitor. There we go. So it is reading in at 800 microfarads. So again, it should be 820, but allowing for 20% tolerances and a very unscientific instrument. That's what we, this is what we expect. And the ESR is 0.06 ohms. So the ESR is the number that I'm interested in. That's the one which I think we're going to see different. But yeah, 800 microfarads, 0.06 ohms. So let's stick in another cap and let's put in one of the ones that didn't look like it had failed and see what that says. If I can fit it in there, I might need to do some jiggling here. Huh. This one seems awfully confused. The ESR is 0.05, which is fine, but apparently that's 1200 mic. I don't know how that is sky high, but yeah. That's a bit odd. Can the capacitance go up on a failed capacitor? Don't know. Okay. What about the one that's totally failed, the bulging boy? Let's stick that guy in there and see what that says. Oh, there we go. Look at that. So on this one, with the actual bulging cap, we're down to 330 microfarads, 328, and the ESR is at 3.1 ohms, which is massive. So yeah, so at this point, the VLOS, I'm not sure what VLOS is. Someone in the comments might be able to tell me that. I'm sure they will. However, here we can clearly see a numerical failure in this capacitor. Now that was obvious because the top of it is bulging out and all the rest of it. But here we can see that not only we've seen a physical sign, but now we've got a numerical sign that shows the failure of the capacitor. That's exactly what I wanted to see. Perfect. That was a very successful experiment. Cool, right, so I'm going to go across this board now and remove all the remaining capacitors. I'm not going to bother testing the others. I'm sure there's plenty here, like these ones up here that look completely fine, that are most likely well within spec. However, we'll replace all of them because that was the plan. You know, it seems like these 6.3 820 microfarad capacitors were the problem ones on this board, or maybe it's just these ones that get hammered, who knows. In any case, I'm going to take all of those off the board, so let's hit the fast forwardy section, and I'll see you after the fast forwardy section. Right, I think that's all of them. Let's do a quick count up. So I should have 16 that I've taken off the board. 1, 2. Yep, that's 16 of the caps removed, so that's all good. Right, so now we've got to put some new capacitors on. There we go. That was all right. So what I shall do, I'll put through, that's gone loose where I've pushed all the solder through the hole. So that's very loose. What I'll do is I'll get all the capacitors in and then I'll go through, I'll reflow all of the tips of the legs, then cut them short again. So just for the sake of the demonstration, let's do that on this one, and then we can go into fast forward because again there's 16 of these to do. So we've got that in place. So now I'll flow some fresh solder into that. That joint's gone a little bit frosty. Can we... Yeah, it's because there's still some old solder mixed in there. Right, that's all of our replacement capacitors fitted to the board now, so that's all done. I've fitted all of them. I've tried to leave like a 1/2 or 1 mil gap between the capacitor and the board on each one because you're supposed to give them just a little bit of room so they can expand a little and that kind of thing under heat cycles. Because if you've mashed them down tight to the board, if they expand ever so slightly, they are trying to rip themselves off the board effectively. So we've left just a little gap under each one, and I've reflowed all of the ends of the wires as well. So we've got nice shiny solder joints, and I think we're ready for a test. So I'm going to get the power supply back out and rig this thing back up, and we'll see if any of this was worthwhile in the slightest. Right, we're all plugged in. Here we go. Power supply on. Okay, nothing went bang. That's a good start. And power. No beeps. I mean, this could have a dead CPU in it for all I know. That's the one thing I didn't test for before we started this fiasco. But it's never the CPU. Except when it is. Well, looks like we are nowhere. That makes me very sad. I had a mad hope that we were going to get a successful fix out of this one. I'm going to see if I can track down a different CPU for this. I mean, like, even if it is the CPU, if we put another CPU in there and it works, then sure, we might not, the board may have worked this whole time, but we did still successfully recap it. So that would still be a win in my book. That would still be a learning experience. However, yeah, I got to see if I can find another CPU to see if it's that or whether this board is just stone dead. See you after the cut. Remember, folks, it's never the CPU, except when it is. But it's never the CPU. Get out. This Core 2 Duo cost me the princely sum of £4 and came like this in a jiffy bag. I'm sure this is fine. Which way round does this even go? That way. It's never the CPU. But what if postcard? So Google tells me that E1 is a memory error. But I'm going to take that with a pinch of salt. I will try some different memory in it because I've got some to hand. Yeah, I'm done with this board. We know that it's not detecting RAM correctly, but man, I can't be bothered to continue diagnosing this. Like, we can start looking down the route of diagnosing a board that can't detect memory. But again, I'm just not interested in doing that on just an old board like this. Sentimental value only gets you so far, in short. You know, yeah, I think I've given this a sporting try. I don't know if this video is going to see the light of day because normally I would just be like, I tried to fix something, it didn't work, meh. But I really enjoyed the recapping part. I thought we were really onto something with that. Even if it wasn't, you know, the capacitors may not have been the problem in the first place, the process of actually recapping it and showing the failure mode and stuff like that, I thought that was very interesting. So I would really like to get something out of this video. So I'm going to wrap this video up anyway, and I will edit it together. And if you're watching it, it means I thought there was something worth getting out of it. And I guess submit your guesses as to what's wrong with this thing in the comments down below. As always, my support links will be in the description for my Twitter, Patreon, Discord, and Instagram. And give the video a like if you thought it was good. Thank you very much. I'll see you next time. Bye.